Okay. All right. Hey everyone. Okay, I'm going to talk about what is a manifold today. The talk is going to be split into two things. I'm going to motivate the talk, and during the motivation, I'm probably going to use a lot of language most people in the room are not familiar with. For example, that statement of what a space-time is. But I'm just doing it because I know most of you guys are physics people, and I want physics people to care about manifolds. More generally, geometry and topology. So really, the whole point of the talk is because I realized recently in my physics education how important geometry and topology is in physics. A couple of us thought that algebra was, you know, the holy grail, and it's not. It's in fact geometry and topology, because the algebra that comes in there is through Lie groups, Lie algebras, other things like that. I'm going to try to talk about that kind of stuff. The other part of the talk is that I actually want to be really precise, and I want people to leave here being able to explain to maybe a professor exactly what a manifold is. Because it's one thing to say, oh, it's something that locally looks like, you know, 3 space, locally looks like Euclidean space, and it's something else to be able to tell them what every single word in that statement of space-time is. Okay. The reason why I was hoping that there'd be more freshmen in here was because I kind of prepared the talk in the sense that I wanted people who had not been yet exposed to a lot of higher mathematics to actually be introduced to something in a rigorous way from higher mathematics. I am going to assume some familiarity with, you know, simple set type things, unions, intersections, mappings. I'm going to assume a lot of calculus, differentiability, all that stuff, but that's essentially all you're going to need to know. And I hope that with that said, you'll be able to understand the majority of what I'm going to tell you today. I want everyone walking out of here having learned something. That's the whole point of this. I am going to assume familiarity with this. Is everyone comfortable with this set? Pretty much raise your hand if you're comfortable with Rn. I see some hesitation. Well, I mean, you guys know what, I mean, clearly R2 is just a plane, right? R3 is just 3 space, 3 axes, just can move around in there. And then, I mean, Rn is just change the 3, 10, and n, and you add more positions. Okay, so I'm going to get on to the first part of the talk. Other than assuming familiarity with Rn, what I'm going to talk about today, a clarification I want to make, is that I'm going to talk about smooth manifolds. There's a difference between, there's a lot of different kinds of manifolds, and today I'm going to be talking about a particular class called smooth manifolds. The reason is because you really only need to have an understanding of calculus to understand smooth manifolds. And I think that everybody in here is comfortable with calculus, and so I'm going to proceed in that direction. You can go to a lower level and define topological manifolds, and I'll digress for a moment and tell you what a topology is. The topology on a set is basically the barest notion of space that you can possibly have. The barest notion of a space that you can possibly have is basically what a topology is. I'm not going to give you the definition because it's incredibly transparent, and I don't think anybody's going to learn anything from it. And the reason why I don't want to talk about, you know, the first notion of manifold you're usually introduced to, which is topological manifolds, is because most people in here have probably not been introduced to a lot of topology. Not enough to be able to introduce it in a correct way. But with that said, I do want to say that you could say to someone after this talk that you do know that all smooth manifolds are topological manifolds. It's not necessarily in another direction though. But let me get on to why you guys should study them as physicists. I'm going to only give 2 examples of 2 very large and broad branches of physics, which the notion of a manifold kind of sits at the foundation of. The first is general relativity, and I've written down the formal definition of what a space-time is right there, and I've also written down Einstein's equations and a little remark, but The reason why I wrote it down before the talk is because I want to talk about it rather than explain it. If you know what this means, that's great. If you don't know what this means, it's fine. Hopefully by the end of the talk you'll have a better understanding. But the point I would like to illustrate here is that for a theoretical physicist, if they want to progress general relativity into new directions, new branches, you have to understand the basics. And the basic definition, the first thing you open up any mathematical physics book, advanced book on GR, that's the definition of the space-time is going to be sitting in. If you don't have a good grasp of what a manifold is, at least a smooth manifold, you're going to have a really hard time proceeding from there, right? Now, of course, they have you can learn GR from an undergraduate level, but even if you take the graduate GR, this is going to be one of the things you spend, a couple weeks talking about. Now, there's another point I would like to make with general relativity that goes back to kind of what I was saying in the beginning, is that there's this beautiful relationship between geometry and physics, and the most profound and usually the most canonical example one gives is general relativity. And that is because of Einstein's equations right here, what he arrives at. You don't have to know what any of this means, but what the left-hand side is something completely geometrical. There is nothing entirely, really, honestly, there's nothing physical about it. There's nothing physical. We impose physical constraints based on our intuition on these quantities, what kinds of metrics we can have, and other sorts of things. What's the topology of the underlying manifold? But it is a purely geometric thing. It's a construct of the mathematicians. And on the right-hand side is something physical. That's the energy momentum tensor. That is something that you get from the physics, from E and M. You could have the Faraday tensor sitting on the right-hand side, and you can have other matter fields and etc. So that equation right there is kind of telling you that there is something very deep going on between our kind of mental understanding, our mental construct of geometry, that the mathematicians have spent a very long time trying to lay the groundwork, and how physics reacts to that. And as we all know, the purely geometric notion, which is curvature of a space, is manifested itself as gravity and vice versa. And to me, that is just a profound example for a physicist to study any branch of mathematics. I think that is the most motivation someone can give for wanting to pursue and at least understand some modern geometry, some modern topology. And I say that, and I say geometry and topology, and I would like to make a distinction that I don't think is made enough, but it's kind of pedantic. There's a difference, there's a big difference between geometry and differential topology. When you study general relativity, until you introduce a metric, which most of you guys don't know what that is, but this is just to make a distinction, you're doing topology. Until you have a metric on a space, you're doing topology. You're not doing geometry. That's kind of something that mathematicians like, and I can explain a little bit why that is. Topology is kind of this study of, you could say in a naive way, like continuous deformations of space. Yeah, everybody's heard a torus is the same thing as a coffee cup and vice versa, right? But once you fix a metric, geometry, curvature, things are obviously going to change. The curvature of a torus is going to change if you're going to continuously deform it into a coffee cup. And the geometry is going to change. So, and that's kind of characterized by something called the metric. I just wanted to make that distinction because I honestly don't think it's made enough in physics or math classes, is that there's a difference between geometry and topology, and it's kind of fundamental. And all these quantities, what I'm going to talk about today, are notions from a field called differential topology. So if you really like what I'm going to talk about today, the math department offers a graduate course in differential topology that you should really, really consider taking. It would really solidify your understanding of a lot of this stuff. Okay. The next thing that's a little bit less canonical, which if any of you guys get the chance to take the graduate course with Kennedy, graduate classical mechanics with Kennedy, you're going to learn all about this. But there's another place where manifolds pop up in a very fundamental way, and it's in studying classical dynamics. And I kind of laid out here, how it pops up. But if you consider a system of particles moving in free space, this system of particles, say for example they're restricted to move on a sphere or something like that. This system of particles, the space that it's restricted to move on it's a manifold, and it's called the configuration manifold. Now, let me show you an example, if we can come over here, of exactly what I mean by that. So if we let's say I take a pendulum, okay? Fixed rod of length L, mass M, right? This pendulum is restricted to move on a circle, right? If you imagine that this is just kind of a free pivot point and it can go above the ceiling, right? This is restricted to move on a circle, S1. Now, suppose that this pendulum was a spherical. It was allowed to both swing this way and in and out of the board, right? The configuration manifold of that spherical pendulum is going to be the two-sphere. Understanding the topology and quite possibly the geometry of the two-sphere can help you understand more about the physical system. Clearly, nobody studies the spherical pendulum at that level because you're not going to learn anything. You can get everything you need to know about a spherical pendulum without going to that level. But it's an easy example. It's easy to understand. You can visualize that. Take a double spherical pendulum. A double spherical pendulum is going to have 4 degrees of freedom. There's going to be 2 spherical coordinates for the first part of the pendulum, and there's going to be 2 spherical coordinates for the second part of the pendulum. The configuration manifold of that system is going to be the Cartesian product of two spheres. There's one sphere for the first pendulum, and there's another sphere for the second. Clearly, this doesn't sit in our normal space, in our normal three-dimensional space. You can't draw it on the board. You have no really hope of visualizing this. And this object, topologically, geometrically, is actually fascinating. There's actually conjectures and all kinds of things about, Cartesian products of two spheres and in general, Cartesian product of connected manifolds. And a lot of people don't understand. So the point is, well, let me say something else before I get to the conclusion. Also, a lot of you guys, you're learning, and if you take classical mechanics too, you're learning about Lagrangian mechanics, Hamiltonian mechanics. You learn about the function called the Lagrangian, and then you learn about the function called the Hamiltonian. And hopefully you learned that there's this kind of natural transformation called the Legendre transform to get between these two functions. Well, it turns out that on a manifold, there is a natural space that you can build out off of it called the tangent bundle. And this is where Lagrangian mechanics happens. And correspondingly, where Hamiltonian mechanics happens is something called the cotangent bundle. Understanding these spaces, which are also smooth manifolds in themselves as long as the base manifold is smooth, understanding these two spaces helps you understand the theory of Lagrangian mechanics. It allows you to pull more physics, more equations, more formulas, as long as you want to go along. I mean, Nick and Connor and I took graduate classical mechanics last semester, and we learned all of the beauties of this. It's a fantastic thing. It would be probably kind of interest to tell you a little bit about what a tangent bundle actually is, because it's pretty easy to understand in some senses. That if I take, for example, let me take the circle. If I take the circle, at each point on the circle, there's going to be a tangent line. A unique line that's tangent to that point on the circle, right? Well, you can imagine that, for example, on a two-sphere, at each point you're going to have a tangent plane. And in general, on an n-dimensional manifold, at each point you're going to have a tangent in space. You're going to have something that looks like Rn tangent to each point. Now, if I take all of these tangent spaces, including the manifold, and I just lump them all together, that's the tangent bundle. It's basically, if you want to think it from a physical point of view, if you go back to this system of n particles moving in all three, It's all possible positions of the particles, including all possible velocities, written in a coordinate thing like PV, sorry. This is the position of the particle, and this is the velocity of the particle. And this is the tangent bundle. And so the point is that in a little bit more of a formal way of looking at physical theory like general relativity and classical mechanics, beyond the undergraduate level, if you're a theorist and you really want to understand what's going on, now you might be able to get by without having rigorous definitions under your belt, but I believe that anybody's going to benefit with having the rigorous definitions under their belt. It's just something that it's like, you want to, if you're going to spend your whole life working with a tool, you're going to want to know, exactly how the tool works. You're going to want to know all possibilities of it. It's kind of like using computer software. Eventually, at some point, you're going to have to know everything in the manual, if that's your life, right? So that's that. I think I've motivated enough. I mean, there are people who go on to graduate school in physics, and obviously, math. I don't know about other things. You're going to hear this come up a lot. And like I said, I mean, it's kind of inevitable. If you're going to learn anything of higher mathematics, you're going to encounter the notion of a manifold at some point. Now that I've talked about this enough, and I've talked about it for a perfect amount of time, I can actually talk about manifolds. And it's also, I mean, general relativity and classical mechanics on it. I mean, you can go, just start, all this stuff like string theory and stuff, these manifolds that have non-commutative geometries and all of this stuff, it's just, geometry is just becoming increasingly apparent, to me at least, to be a very important thing to study, if I want to be a very prolific and proficient theoretical physicist. All right. Well, okay, now that I've spent kind of rambling on about this for a little while, I hope I've got you guys a little bit interested in learning about this. Let me start to be a little bit more mathematical and a little bit more sophisticated. All right. So I'm going to give right now, in fact, the definition of a smooth manifold. And then I'm going to spend a little bit of time breaking down the definition and explaining each little piece of mathematics, why it's there, and why it makes sense. So first of all, before I start writing, we all kind of have a notion of a surface sitting in 3 space, right? There's this kind of bumpy thing, like if you were to map out kind of like a rough sketch of the mountains on the Earth and kind of feel it around. That's kind of a surface sitting in 3 space. Or if you just want to be precise, think of a sphere. Think of a sphere sitting at the origin, right? And imagine that you're a tiny, tiny little bug sitting on the surface of the sphere. Now, there's something really special about a sphere, about a surface that we want to generalize. And that is the fact that when you're close enough to a sphere, think about us living on Earth, it looks like you're on a plane, right? If you're close enough to a sphere, the space looks two-dimensional. And that's kind of one of the key points, but there's something else. There's something else in that. It's that physics is kind of, physics, mathematics, and if you're doing geometry, it's all about a coordinate system. You want a reference frame to something, to kind of speak in layman's terms, right? You want to pick an origin, and you want to be able to, for example, in R2, we have this really nice thing where we have these kind of grid drawn, and we know exactly where we are when we're at this point relative to this point, because we call this distance 1 and this distance 1, so you go, and you find that you're at 2, 2, right? Well, clearly there's other kinds of coordinate systems. You have spherical coordinates, you can get weird ellipsoidal coordinates, toroidal coordinates, all of these other things like this. But the point is that on a sphere, it is not possible to cover the entire sphere with one smooth coordinate system. And so that means that you're going to have to patch together coordinate systems in order to be able to do mathematics to study a sphere. And I'm going to explain all of this in a really precise way in a moment. So that's what we want to generalize. We want to generalize the sphere in the sense that it's going to be a space that we use these kind of coordinate patches sewed together, and if we want it to be so that if we're close enough in one of these coordinate patches, it looks locally like, for example, with the sphere, a two-dimensional space, or in general, an n-dimensional space. Okay, so how are we going to do this? By the way, while I'm writing, does anyone have any questions? Really, someone come up with a question because I'm going to be writing for a while.
Okay, well then could you kind of say what you mean when you say that you can't just cover a sphere with one nice,
You kind of all around coordinate system?
Yeah.
Well, okay, it's not exactly the same thing, but let's think about a different problem. I think recently there was some talk on the SPS page about the Harry Ball theorem.
Yeah.
Right, with the sphere. It's kind of the same idea. You can't have, what the Harry Ball theorem says is that you can't have a vector field over, you can't comb a hairy ball down such that at all places the hair is smooth and flat on the ball. You're going to have somewhere where there's a cowlick, right, if you're thinking about a head of hair. And, well, if you thought of each piece of hair as a vector, what it says is that, you can't have a globally, and on the entire sphere, you can't have a globally defined smooth vector field which is non-vanishing at every point. Okay? Now, I'm going to get to explaining some of that a little bit later, but that's a different problem, but I think it gives you some intuition a little bit for the same thing with the coordinate chart thing. Okay? An easier example, I would say, since I'm doing good on time, is a circle. Okay? Now, clearly, on a circle, I can try to cover it with one chart. I can try to cover it with a line segment if the circle's circumference is 2 pi. I can try to cover it with a line segment whose length is 2 pi, right? But there's going to be a problem at the endpoints, in that the function that takes this line to the circle cannot be one-to-one at the endpoints. There cannot be a one-to-one correspondent, and specifically because of the point, as I wrap this around here, 2 points are going to have to lay on top of each other. That's the problem. Okay. That's why you need to have 2 lines separately, for example, one that's pi over 2, and another one that's pi over 2, that overlap each other. Like this. Okay? And on these overlaps, you want the function that takes this half line to this half line to be differentiable. And I'm going to define all this, but can you see that? Yeah. It comes out of the requirement for what we want a manifold to be, and we want that function to be one-to-one. If anyone has any more questions? Guys, it's quiet. I still got a little ways to go. It's not a short definition. So really, you guys just want to talk or anything?
What is Hausdorff?
So what Hausdorff means is that if I take any 2 points in the space, I can find 2 open, but that doesn't really matter. I can find two open sets that are disjoint such that one point lies in one and another point lies in another. So I don't have a very easy or natural example of a non-Anaxagoras space. Actually, a good example that you can think about is the cone at 2 points. The problem of Hazeldoorf. That's two cones sitting at their vertices.
Is there any relationship between the values over the open set and the values over the exterior of a manifold?
What do you mean?
You just said it's an open set, so is there any relationship between anything taken over the any integral or anything taken over a manifold, over the surface of a manifold, and anything taken over its exterior?
Well, yeah, but I mean, it's an open set. I'm not sure entirely how.
What I mean?
Yeah, I'm not necessarily.
Well, let's say you have a manifold that's a single line.
Okay.
Is there any relationship between anything taken over, any value evaluated over the line, such as its area or whatever, and the exterior of itself?
So are you saying that, for example, if I take an open set on the line and I take the area of that open set, it's equal to the area of the manifold minus the exterior or something like that? Is that what you're asking?
Sort of, not exactly, but you could think of it that way.
Well, you got time.
So let's say you have a line, and its value, and you integrate just over the line, just like the number 1 over the line.
Okay.
Is there any relationship between that and the endpoints of the line?
No.
All right then.
Pretty straightforward.
So it's not the difference of the exterior ones.
No, because I mean, a finite dimensional set's going to have a point is going to have no area.
No,
No.
I'm not saying the integral of the points.
I think I get what you're saying, but that depends on the measure as well. You have to like define a measure over it. You're saying the difference of the
And a measure of any
Yes,
finite
it's-
set is 0.
Oh, and
Measure of any finite set, measure of a point is 0 always. Measure of any finite set. I'm not. You can ask me later if you figure out another way to ask me the question. But in the sense of relationships to open sets, all that means is that it's open under the notion of whatever topology you have on the manifold. So it's not necessarily the metric topology, where it's open in the sense of you have some distance function on the manifold. I mean, it has a natural topology which is induced from Rn, but which can be whatever topology still. It doesn't have to be a metric topology. Alright guys, we're almost there. Don't worry.
Can you play this with thermodynamics?
Huh?
Can you play this with thermodynamics?
Did I close?
Can you apply it to thermodynamics?
I have no idea. I think that,
well, this definition got really intense toward the end.
Is a manifold strictly limited to, say, a constraint, or does it mean something other than that, like a field or a, I don't know.
what do you mean?
Like if
Is it restricted to Rn?
is it, well, when you have a physics problem, is the manifold the constraint?
Yeah, it characterizes the constraint of the system. So that's why it's kind of called the configuration manifold. It's also called the configuration space. So like, for example, for example, if I'm, the pendulum example I gave, the constraint on that system is that it can't leave that distance R, L, or whatever the length of the rod is, it can't leave that distance away from the pivot point. So the manifold, in a very kind of precise way, maybe that's not the right word, in kind of a natural way characterizes the constraint of that system, in the sense that for the pendulum, two-dimensional pendulum, the configuration manifold is a circle, right? And that's characterized, the reason why it's a circle is because that mass, which is the particle you care about, right? You care about the motion of that particle, is constrained to move on the surface of the circle. Do you see that, right? Because it carries around a circle of radius L, or whatever the length of the rod of the pendulum is. So yes. That's where this whole theory of classical mechanics comes in. I mean, and you have like really exotic systems. I mean, I think one time we had like an n-dimensional harmonic oscillator constrained to the surface of a sphere. N-dimensional sphere. So yeah, I mean, it gets a little wild, and I mean, toruses come up a lot. If you get the chance, I mean, I know you're kind of far along. If you get the chance to take a graduate classical mechanics course, you really should. It's a great class, and you don't only just learn, manifoldy stuff. You bring some together really well.
You foliate your torus.
Yeah, you foliate things, which is fun.
Can you explain foliate?
I can at the end. But let me get on to one. So I want everyone to read that definition. I want you to tell me if it scares you.
Yes.
If it scares you. Okay, let me explain.
Looks incomplete.
It is because I got lazy.
Okay.
It is because I got lazy, and the last condition is purely technical. It says that I'm gonna explain it whenever I get there. Okay. I wish we picked the right color. All right. And now I'm gonna draw this. I'm opening up my awesome. By the way, guys, if I actually spark interest in anybody, I can drown you in textbooks to study this stuff. So, yeah, we can do that.
Is that the original or is that the translation?
It's translated. I can't read. Okay, what is it? Common Spanish?
It's Portuguese.
Portuguese? Oh, Brad. I'm going to talk again in a second, I promise. You might want to cut this out of the video, Connor.
Nope, they're going to get every beautiful second.
So could you explain family?
It just means that collection. That family is just saying this collection. This is a set.
Family means nobody gets left behind.
Start regularly incorporating Ohana.
You should write the next math test you have.
I don't have math tests anymore.
You're lucky, aren't you?
Cool kid. You already took them all.
I did. I am
Ran out. You're so lucky you graduated.
You're graduating too, I'm pretty sure.
I'm not graduating until summer.
Never mind.
Correct.
And that's only if I'm lucky enough to pass senior design.
Awesome. All right. Well, here, clearly due to dimensionality restrictions, what I drew on the board is a picture of a two-dimensional manifold. This definition is an n-dimensional manifold. Okay, so a smooth manifold of dimension n is a set M together with a family, just a collection of these things right here. U1, X1, comma, U to It's a collection of these things. This is a map. This is a set of mappings, X alpha. So the alpha tells us what set the mapping corresponds to. Now this set, it's a subset of Rn. Now everyone here can look at this picture and just think of n is equal to 2 when they're reading this definition. Okay? So X alpha, U alpha maps to the set M of open sets. Don't worry about that word. It's not going to hurt you if you don't understand it. Of subsets of Rn such that if I, take the collection of all of the images of these sets, it's going to equal the whole manifold. And that on the intersections of these patches, which I called coordinate charts earlier in the first place, I'm going to explain that. The transition mapping between these two coordinate patches is going to be differentiable. And that's something that's kind of extremely fundamental. And it was actually when people were trying to develop the definition of a smooth manifold, they were having trouble because they didn't realize how important that transition part was. So what we're looking at here is, let's take a step back at this definition and let's look at this picture I've drawn here. I've drawn a two-dimensional manifold. Okay, now this is going to be everyone in here, this notation, right here, x beta of u beta, it means the image of x of that set. So it's all of the points in M that x maps to, and which I've kind of diagrammatically shown is this kind of loop thing sitting on the manifold. These are all of the points that x sends from this set to here. It's just that kind of thing. Now, it's on this set here, because this is in R2. Okay? This is in R2. This is intrinsic. This isn't sitting in some ambient space. And on R2, we have natural coordinates. Okay? Now, these coordinates, this is kind of a coordinate patch sitting in R2, like you would usually think. It's kind of just a nice little grid sitting in a plane, and we're going to take that grid and we're going to put it over our manifold in some way. And that's what that mapping is doing, is it's taking this grid, this subset of R2, and it's folding it on top of the manifold. It's just kind of fitting it there. And that's going to be our coordinate patch. That's going to be our little local area that we can do computations in. And it's the same thing with here. Here's another set. This is, I'm just labeling it. This is a subset of R2, U alpha. It has coordinates on it too, just like R2 has coordinates. And I'm looking at the image of this set under this map in the manifold, which is this thing right here. And it's just a coordinate patch on the manifold. It's the exact same thing I just did the example with the circle. It's I take half a line and I fold it over half the circle. And if I'm sitting in that half line on the circle, that's my little coordinate patch. If I was in one dimension, that would be an example. X would be a map from the half line onto a circle. Its image would be that bent shape sitting on the arc of the circle. And that's where I can use my very kind of trivial and natural coordinates from R, the real line, to do all of the things that I can already do in R. Differentiate, integrate, calculate lengths of curves, etc. And this is just the two-dimensional extension. So, for example, let me take the sphere take the sphere. Now, on the sphere, let's say I take a patch from R2 and I lay it over the top of the sphere. x. I've taken this patch in R2 and I've just laid it over the sphere. So now I've given my sphere a natural set of coordinates. People kind of trying to see a little bit what I'm doing? Now, if I take the collection of all of these patches over a manifold, if I take the collection of all these patches, because there's going to be many. I've only drawn 2, but there's going to be many, many, many of them. If I take the collection of all these patches, clearly it has to be the whole manifold, or I haven't accounted for everything. So if I take the collection of all the patches that I'm going to use to cover the sphere with coordinates, it's going to have to be the whole manifold. That's kind of the easy part. The harder part is understanding what this statement means. This statement means that as a function from here to here, which I write as x inverse composed with x inverse of alpha composed with x inverse of beta, this map needs to be what is called a diffeomorphism. That's kind of, it's a scary word, but it just means that it's a differentiable mapping that's bijective and has a differentiable inverse. And that means that I can smoothly go from this coordinate system to this coordinate system while staying on the manifold. Okay? Now, let's see here. Right? So this is going to take this map here. It's going to take a point from this set. It's going to send it to its point here on the manifold. Okay? It's going to take a point P here. It's going to send it to its point on the manifold. And then it's going to take the inverse mapping and send, well, this point's going to have to be in this overlap. And it's going to send it to this point here. And we're going to do that for all points on that overlap. And that's going to have to be differentiable. And that's kind of this key thing, is that if I'm going to lay these coordinates over the manifold, I need to be able to walk from one coordinate system to another in a smooth way. Just think of it naively. Think of it physically. Think that there's no kinks when going from one coordinate system to the other. I have one coordinate line and I have another. I want to be able to walk along that coordinate line without taking, sharp turns, sharp corners, things like that. Right? Something just incredibly, you come up with some like incredibly silly, convoluted coordinate patch and you could get something like that. And so this is what this is saying right here. Now, I'm going to speak just kind of in map terms, and if you don't understand everything, you can ask me after the talk exactly what everything means here. Because I'm not sure how used to everybody is with set intersections and the empty set and open sets and etc. But what it's saying is that the image under this set in Rn, which remember this is all n-dimensional, but over there is 2. If the image of this set in Rn intersection, the image of this set is not the empty set. That means that these two images are not disjoint. That W here is this that I've labeled on the manifold, right? If that's not the empty set, and you can kind of ignore this for a brief moment, and that X inverse is an open subset of Rn, then that mapping that I've just talked about is going to be smooth. The third condition says that this family is going to be maximal relative to the first two. It just basically means that that coordinate chart thing that I've done is off. Or it includes the optimal coordinate chart. That one's a little bit harder to explain. Now, I've basically said that definition, but that's what people call them in coordinate patches. Now, these coordinate patches, which I've just introduced you to, which is basically just, for example, the image of one of these sets under the mapping, this is kind of why it's so important. Like, for example, why are smooth manifolds what's picked to represent space-time? And that's, for example, one of the motivations was the equivalence principle. The equivalence principle can be restated in a purely mathematical language by saying that in a small enough region of space-time, everything looks Minkowski. People who have had relativity know this is the equivalence principle, right? It's rephrased in different ways, inertial mass equals gravitational mass, etc. But that is exactly what it is from a formal point of view. It's that if I take a small enough region of my space-time manifold, like I've done here, I'm going to be sitting in a coordinate chart. And just like in that coordinate chart, I'm not going to be able to distinguish between the manifold and Rn. When in the case of space-time, I'm not going to be able to distinguish between, whatever space I'm actually in Minkowski space. The space-time manifolds that are used, the manifolds that are used in general relativity are a little bit more complicated because, they have this kind of weird, as physicists know it, they have this weird metric signature. I don't have the time to talk about metrics today, but if you're interested, I can explain them briefly after. But that just kind of, you're halfway there to understanding that statement of spacetime that I had there earlier. If you pass by the C infinity just means smooth. I had that up there. And Hasidorff just means what I had told Nick earlier, that if I take 2 points in my space, I can find sets that are disjoint, which only contain either point. And I'm pretty sure that was it. So I'm running out of time, but that's essentially it. Let me stop here and just see if anybody has any questions or wants me to go a little bit further with explaining a concept or a topic. I do know quite a bit about this stuff, a lot more than what I just introduced here, so I think I can answer more technical questions. Anyone get any questions?
Can you talk more about how it's like?
Okay. Let me do this for the point. This is essentially what Hasidorff means. I take a point here, and I take a point here. I can find a set here, and I can find a set here, U, V, such that U intersect V is an empty set. It only contains. Hasidorff is just kind of generalizing this. That's what it means.
Why do we want that?
It's natural.
And spheres?
Yeah. Just need a two-sphere. Take a point on a two-sphere. Take an open set. Well, that's the thing is that you have to, in order to really understand the Hasidorff axiom for a manifold, which is an axiom for a topological manifold. In order to really understand that, you need to understand what a topology of a set is. And it is, to be honest, I've read Map Overflow posts where literally the post was, can someone please here tell me how I explain to my students what a topology is? Because it is the most incredibly transparent notion. It is literally the barest notion of space that you can put on a set. You have a set of elements, totally arbitrary, and I want to put structure on that. What's the barest notion of space that I can put on that set? That's what a topology is. And elements of the topology are open sets, but they don't have to be necessarily open to your intuition. Right now, your intuition of open is, without the boundary. You have a set in Rn and you take an open ball, right? It's just the ball, it's all the points that are less than or equal, that are less than radius r from the point. Pretty much what I've just drawn here, except minus the boundary. It's a circle minus the boundary, sitting in a point, okay? And the thing is that those are open sets under what I've called the metric topology. In general, open sets can be just incredibly strange. So that's why if you want to ask this question, the Hasidorff axiom on the n-sphere, yeah, of course, n-sphere is a topological manifold. It has to necessarily be Hasidorff. If you already know that the n-sphere is a topological manifold, if you're not trying to prove it, then you know it's Hasidorff, because that's one of the conditions it has to satisfy. Topological manifold. So you don't have any other questions?
How do you generalize or have an n-dimensional sphere?
Yeah. Oh, this is a great question. I wrote S2. So, what is a unit circle? It's a circle sitting at the origin in the plane that all the points on the circle have distance 1 from the origin, right? What is a unit sphere? It's the set of all points in R3 that are distance 1 from the origin. Let's just generalize this. I'll do it over here. The generalization is, we call the set is called Sn. The generalization is, if I take, it's the set of all tuples, right, x1 through Sn. The examples I was just giving, replace n with 2 or 2 or 3, such that, you know it as the Euclidean norm. The sum of xi squared equals 1. That's the n sphere. If you put, sorry, I need n plus 1. Right? Because the 2 sphere is a 2-dimensional manifold sitting in a 3-dimensional space. 2 spheres sitting in R3, right? You have three degrees of freedom, if you're thinking like a physicist. But the 2 sphere, if I'm sitting on the surface, I only have 2 degrees of freedom. Okay. That's how I generalize right there. If you replace n with 2, you get the unit sphere. You replace n with 1, you get the unit circle. If you replace n with 0, you just get 2 points. It's a 0-dimensional disconnected manifold. 2 points, it's just the point 1 to 1 and 1. There's all kinds of generalizations of this. String theory uses something called orbifolds, which these sets that you're mapping to your set aren't necessarily Rn. You're like modding out by some group structure, like for example, you're modding out by like Zn or something like that. You're doing something really weird. There's complex manifolds where I replace my Rn with Cn. People know what the complex space is. C is just, your complex plane, I on the y-axis, real on the x-axis. And, you keep going from there. The complex manifolds are what show up in quantum mechanics. Real manifolds are what you're going to be doing in classical mechanics and general relativity. But, yeah. Is there any other questions? Really? No questions. All right.
Thank you.